Hi, I'm Justin G0KSC of innovantennas.com and G0KSC.co.uk. Innovantennas.com is my business site where we make ham antennas and commercial antennas for all sorts of purposes. G0KSC.co.uk has a lot of my very early work from sort of 10 or 15 years ago, and it's there for you to build antennas for ham radio for free for personal use. That's that bit out of the way. What we're going to cover today is the 33-foot vertical, why it works and why it doesn't. Basically, between 40 meters and 17 meters, you get some really good DX low angle of radiation. Above that, not so good. Stay with me and we're going to find out exactly why. Okay, so welcome back, and we're going to get straight into it now. What I've done here is I have some models in EasyNet, and we have the 33-foot vertical, and then I also have a 66-foot centre-fed dipole that's vertical, in order that we can do some comparisons between the two. We're using EasyNet because it works very quickly, just basically on wires, doesn't take into account any other factors around the antenna. But the simulations that it does are very fast, so that works for us very well. And then what we can do is, or I should say that the NEC 5 engine that's in there is also extremely accurate as well. So what we can do is we can do some very fast comparisons and see exactly what's going on. So how do the pair look? This is how the 66-foot vertical looks. A black line with the red dot in the middle and lots of green dots. And then the pink line is a representation of the current distribution through that element. The round circle is a representation of the feed point. And the green dots are segmentation pieces, if you like, and they are measurement points where voltage and current are measured along the lengths of the element in order to establish how performance is going to be. So a little bit more complicated in the vertical, because we now have some radials. I'm just going to back this out so you can see. And I've got 8 radials on here, then the vertical section, and you'll see it's just above ground with a small connection here as well. So the configuration and why I'm doing this is, if I was installing a 33-foot vertical, this is exactly how I would do it to ensure the best performance I can for the number of radials, and also to have it so that it's fairly safe to operate. So why do I say safe? The reason for that is that it may not be immediately clear, but the red lines here, the Y and the X axis, are ground, and you can see that the elevated radials are of course just above ground. This is the best way to do it, rather than to bury them or have them in ground. Obviously it's very difficult to do, but if that's insulated wire and it's laid on the ground, similar kind of effect. And then underneath here, when we zoom back in, you can see there is a wire that takes it down to ground, and this would be an earth state. However, you will see that we have certainly do have a round circle, which is representative of the feed point here, but you'll also see that there's a box. There's a square box there as well. So why is that? Well, the box is a representation of the fact that there is a coil in here as well, and that coil is an RF choke. So basically, the braid side of the coax that's feeding the antenna is connected to the radials, and then the radials, just bear with me for a second, I'm just going to pull these pink lines off, and then the radials themselves are, or on the other side of the radials and the braid, is the RF choke, which is a coil of wire, and then that is connected to this section which is going to connect down to earth. So why is that in place? One of the points of note at this stage which we need to make is, I'm going to look back at the vertical dipole again. So this is placed just above ground. You can't see it very easily in here, but this antenna doesn't go all the way down to ground. It's actually spaced above ground by 0.5 of a meter. And when the antenna is in use, it's fed in the center, and you've got one side is connected to the inner core of your coax, the other side to the outer core. Now, when you have a vertical with radials, as we have here, you have the vertical section, which is the same as the vertical dipole, and the vertical section here is connected to the center core of the coax. The braid side is connected to all of these wires that are facing out here. Now, what they're doing is they are providing a mirror effect off of the vertical section in order to replicate the bottom section of the vertical dipole that we was looking at. It can't go straight into ground because ground's in the way, so it's spread out across ground in order to mirror image the vertical section. And this is why you may have heard it and you may not. Depends on how much time you've spent in verticals, but the more radials you've got, the better. Well, it gets to a point where you can add them, and yes, it does increase, but it's not sort of linear returns. You get less and less benefit the more you add. And the reason that I've got 8 here is that's kind of where it gets to a reasonable level of return. So what's the compromise if you have less rather than more? Well, I mentioned the mirror effect. If you imagine that the less radials you have, the less reflective that mirror is, and then the less performance that you would see as a result. More of that escapes through to ground. So coming back to the coil and the ground connection that we spoke about, if I were to just connect the braid to all of these radials and then to a ground post which is earthed to ground, then a lot of that current, rather than dissipating and illuminating those radials to give us that reflection effect, will be dissipated or go directly to ground and lost, reducing the efficiency of the vertical. So what the choke does, the choke is designed to make a block, or like a cut mark if you like, at the design frequency. So the RF doesn't see a ground connection. But for DC purposes, like static build-up, which will be direct current rather than alternating, it sees no choke whatsoever, so it can leak down to ground safely. But again, at the frequencies that we're talking about here, 7 megahertz up to say 18 megahertz or so, the choke will block that ability to go down to earth. So you've got a win-win. You retain the efficiency as if you didn't have this ground connection here, but you have the benefits of having the drain down to ground and all of the other associated benefits there are of having the coax grounded at the feed point end of the supply, or the supplying coax. So that's that section. Now this is the section which we add the loads into here, and you'll see that the impedance, or choking impedance if you like, here is 400 ohm. Now there's a good reason for that. We can have between 500 and 250 and 500. The reason I've chosen the 400 mark is that gives us an effective choking range of around 5.5 megahertz up to around say 15 to 20 depending on the spacing between the turns. So we can achieve that 17 meters block as well. Above that, because the performance isn't so good, which we'll see in a few seconds, then it's not such it doesn't matter really about the choking not being viable there. I have produced a document which explains this side of it and how it's calculated, and yes, there is lots of maths in there just for the theorists amongst us to have a look at and tell me where I'm going wrong. But ultimately at the bottom it then gives you the sizes and the measures that you need to make. Now I have one of these. It's like what I prepared earlier. These things you can get off of Amazon or AliExpress for about 20 quid, and this can measure inductance. Got this couple of little clips here which you would clip each side of a coil, so if you need a certain inductance, which we can calculate from the formulas, and that will be in the documentation, we can assess to make sure that the coil is working as and in the right specifications, and then attach that between our connection of the braid and the radials and any earthing stake. And that's one of the biggest issues that people have, one of the biggest failures or mistakes taken out of the equation as far as our vertical is concerned. The next thing we're going to cover off here is the ground type and ground conductivity. Now that's in here. Now what I have done is I live in a place called Canvey Island in Essex in the UK, and it's clay soil, and I'm in the middle of suburbia, so I'm surrounded by concrete. So the configuration within here has been set to align with my surroundings, where I'm going to get a lot of RF absorption from buildings and stuff. So in some cases, when you're in open fields and things, you would get slightly, we would be able to adjust that up and you'd get slightly better performance. So let's have a look and see what this 33-foot vertical will give us in terms of footprint and gain from running at the 7.1 megahertz. So this is it. So you can see it's not too bad at all. The cursor angle, or the main point of gain, is 26 degrees. So really not too bad from a frequency perspective. But if you consider that the reference gain in dBi, an isotropic radiator, is 2.15 dB, which is 0 dBd of a dipole above ground. Now, one of the reasons, there's a lot of debate about why people use dBd and dBi. Let me just explain that quickly. dBi is a free space measurement, so for comparing one antenna against another, it's the ideal method of doing so. dBd is placed when an antenna is placed above ground. Now, depending on an antenna's placement above ground and the type of ground, conductivity, distance, etc., that gain will change. So if you're talking about something in dBi, it needs to have referenced with it the ground type and the distance above ground, rather than just a dBd figure. Otherwise it's pointless, and that's why the dBi measurement is used. So a dipole would be a normal dipole would be, say, 2.15, but you can see here it's minus 0.3, and that's due in a lesser or larger extent due to the losses that you would get from from the ground type and it being fairly poor. It's not wholly representative of just having a vertical like this with radials, because if I put I'll show you the 33-foot vertical, sorry, the 66-foot vertical dipole that's center fed. Let's just go have a look at that for a moment, actually, because it doesn't particularly look as if it's center. Oh, it is center. So this is how that would look. You would see, because the effective height of the center of the antenna, bearing in mind on the vertical with radials, the center of the antenna is almost at ground level, and we have that mirror imaged second half which is below ground. On the vertical dipole, the same point is already over a quarter wave above ground, so it has kind of a height advantage. So in that respect, and of course the center fed 66-foot vertical really isn't practical at all. So in that respect, that's the reason that the angle of radiation is lower, because the biggest controlling influence over angle of radiation isn't the type of antenna that it is, or the type of beam, or whether it's a quad or a Yagi or whatever. It's the height above ground. There is some bias which is placed on the number of element series on a Yagi or a quad, and a quad would show as having slightly lower angle of radiation, simply for the fact that the mean height is the center of the quad rather than the bottom of the quad, whereas the Yagi, it's got no depth to it, as it were. Anyway, I'm digressing. So that's 19 degrees, and you can see it's plus 0.07 dB. Again, partly because of the ground proximity thing, but of course because of my lossy ground it isn't up to the kind of levels that you might otherwise expect. Now what I'm going to do is I'm going to increase frequency on each of these so you can just get an indication and compare between the two. As I've said, the vertical 66-foot centre fed isn't practical. This is just a point of reference to show you how well the radialed vertical quarter wave rather than a centre fed vertical half wave dipole can compare in the real world. So I'll firstly change the 66-foot vertical to 10.1 so we can have a look on 30 meters, and on 30 meters it looks very different and it's gone to 0.72. You can see we've lost a lot of that would be lost RF going upwards, and that's now transferred into side to side, which has effectively given us that extra gain. So the next one is on the vertical, 33-foot vertical. So we run the polar plot on that, and a slight improvement is still below 0 on the dB mark, but the radiation degree has changed a little. You know, it's improved, but of course it's still down on the antenna that would be much higher up in band. We go on to 14 quickly and look at this one, and I'll do the same on here. Dot 1, and we can see the comparisons here again. Now the 33-foot vertical is kind of looking better, because what you would see now is the vertical dipole, because of the configuration and where it is, you have this secondary set of lobes, which is a pattern breakup in the or the elevation plane, is something that's induced through height above ground. The higher you go above ground, the more pattern breakup you will get. So the advantage of the vertical in this case is because it's at ground level, it's keeping these lobes a little more compact without the secondary lobe, and that in turn has meant that you're starting to get an increase in gain out to the side. So on this one, the vertical dipole is now dropped. It's minus 2.08 dBi, yet the 33-foot vertical, where it's effectively an end-fed half wave with now radials, has gone up to 0.47, so you've got half a dB of gain here. So how's that going to translate when we get up to 18? So this is the vertical, the centre-fed 66-foot vertically polarised dipole, and you can see we've got now an accentuation of that vertical lobe, and it's now starting to get very high. The lower one isn't too bad at 10 degrees, and oddly it's swapped again, 2.87 dB, because of course these smaller lobes have become compressed, and as you compress these lobes, that's where the gain comes from. It's like, just, I'm going to digress a bit here, but when you have two antennas that you stack and you get more gain, the gain is coming from the compression of the lobe in the direction of the stack. So if you have two Yagis, two 5 elements, and the beam width was say 60 degrees, two of them stacked together would have up to a 3 dB advantage in terms of gain over a single, but the beam width would have been cut almost in half, sometimes a little bit more than half. It depends on the stacking distance exactly. So let's have a look at the 18.1 now on the vertical. Now, I mentioned earlier on about the performance being reasonable up to 18 megahertz and then not beyond. So why is that? As you can see here, you've got some butterfly petal kind of lobes here. Yes, the angle of radiation is relatively good at 16 degrees, and there's 3 dBi of gain, but there's also some very high lobes here. So something like this 33-foot vertical on 17 meters would be great for short distance stuff, for local stuff, like for me into working into Europe, because of this lobe up here, and it would be excellent for DX as well because of the low angular radiation. And what we typically look at with an antenna is the 3 dB beam width. Now the 3 dB beam width on these two antennas is represented by these pink marks. So the 3 dB beam width means the maximum amount of gain and up to 3 dB below that. Now on the vertical dipole you can see that 3 dB beam width is like 13 degrees. So it's really narrow. So that would only be good for DX. The 17 meter one, it's extremely wide, 60 degrees, 60. So that's all your local stuff, European, mid DX, long DX, and everything you can think of. So before I go into the explanations again here, let's put this up to 21 megahertz. I'll do 21.1 in order we can get some indication. Now where's my second EasyNet gone to? Oh, there it is. 21.1. Boom. Now 66 foot centre fed, 33 foot with radials. What do we note? There's extremely high lobe angles, and although the 3 dB beam width is still wide on the 33 foot vertical compared to this, and gain's pretty good, or the best it's been, it's at a very high angular radiation, 46 degrees and 44 degrees on this one. So for me in the UK, I'm not going to get any DX. I'm going to be working into Europe, and that's it. I'm not going to hear the stuff that's long distance. So what's the problem? Basically, we have three configurations of antenna. You have a quarter wave or for element sections, quarter wave, half wave, and 5/8. If a single uninterrupted element section is longer than a 5/8, then the lobe angle will start to increase until, if it's in a vertical, it's beaming straight up. And that's the whole concept of things like a beverage, which is a very long wire close to ground. It gives a beam-like directivity in the direction that the wire is running. And it's also why some people that have, you know, an 80 meter dipole, and they're working some excellent DX on 6 meters, but only in some directions. And that's because rather than firing out to the sides with nice big wide lobes, they've now got very small beam-like lobes off of the ends of each end of the wire. So you could still work, and you would get a good SWR. In actual fact, on a 33 foot vertical on 21 megahertz, you wouldn't need any form of tuning or matching at the base of it. It would just be a simple feed, and you would probably get a respectable SWR without. So what happens if we go now to 24? Let's go to 24.9 on this one, and we'll run that. Oh, hang on a minute, what am I doing? I'm not doing SWR. 4.9. Now that's a really odd looking pattern. And 24.9. Now this is also the reason why a lot of you would have like the EFHW verticals that will tune and show a good SWR up to say 4 meters. Can't hear anything. There's nothing ever there, the same as on 6 meters. There's all these people saying that they're hearing this DX on 6 meters from everywhere, and you can't hear anything. It's because your signal that you're going to be receiving are coming from straight up. If you had a satellite going overhead that was on 6 meters or 4 meters, you would hear that okay, but you're not going to hear anything from either side of the antenna. You can see now this has gone up to ridiculous levels. We're still only at 12 meter band, and it's now 39 degrees angular radiation and 35 on this one. So we go up to 28.1, and we'll run that. And now we're starting to get that pattern breakup. And 28.1 on this one, and run again. And we've got a slight change now back to the 34 degrees, but still extremely high angular radiation. So you know, that's it on this side really. I'm going to go into some of the tuning aspects and what we can do in order to counteract these issues in a later video, if this is something that there's enough interest in. I do enjoy the comments, and it's nice to see what you'd like to hear and discuss. But one of the things that we can do is we can add smaller wire elements to a 33-foot vertical to take some of these issues away, and there's a very simple way of doing that. The other thing that's a point of note is that the ideal scenario is one where these antennas have some form of antenna tuner unit at the base. On my antennas, and I've used both the 33 and the 43-foot vertical, I've used one of the MFJ remote outside tuners connected directly to the vertical antenna at the base, and then I can auto tune it from indoors. We've got to keep in mind that the correct and only real place that an ATU should be placed is at the base of the antenna. ATUs that are placed inside radios were put that way when radios first went to solid state PA devices because of their sensitivity. They could blow very easily. So they were placed there in order to correct the impedance, that any impedance mismatches there might have been, in order to protect the PA. Now we've kind of got a little bit lazy and started to tune things at the antenna end, and whilst there's a lot of theories and opinions on this, but basically if you've got a 25% return from a 3-to-1 SWR, although you make it look good with the ATU for your antenna or for your radio so that you can still put a lot of power into the antenna, there's a lot of odd impedances far and away from 50 ohm that are now being presented in that coax, 50 ohm coax, and some very high voltages as well, and you're still not going to get the kind of radiating efficiency that you would have had if you'd have tuned the antenna. So again, that's for another subject, but I think that's pretty much everything that I needed to cover today. Hopefully that's opened your eyes up into what happens with an antenna like this, and maybe even some of you, and you could let me know in the comments, have had something like a 33-foot or a 43-foot vertical and experienced this on the upper bands where it doesn't perform quite the same. And of course the thing is if you had the 43-foot vertical, you'd be able to use 60 meters, which is great, but then that half wave point is now 30 meters instead of 20 meters, and what you got on 18 meters on here you would now get on 20, so even 18 meters, 18 megahertz. So of course on the 43-foot vertical, 18 megahertz is now out of the frame. It's very high angular radiation. So again, thanks for watching today. If you liked what you've seen, then please like and follow, and I hope to see you on the next one. Cheers for now.